Hello everyone. Today we are going to discuss about molecular orbital theory. So in our previous lecture we have discussed about the crystal field theory. Crystal field theory actually describes the bonding in coordination complexes, but it has few difficulties. That is the assumption based or the assumption on which crystal field theory was proposed, that is the ions, the metal and ligands are considered as the point charges. So the crystal field theory only considers electrostatic interaction, that is ionic bond between the ligands and metals, but so it does not consider any orbital overlapping or covalency in bonding. But actually, if we see the coordination compounds, there is coordinate covalent bond is formed between the metal and the ligand. So crystal field theory actually is not suitable for the coordination compounds. So the bonding in coordination compounds can be better understood through molecular orbital theory. Later on, molecular orbital theory was proposed. It explains the chemical bonding through the overlapping of the orbitals, where delocalized electrons can be easily described, and also from molecular orbital theory we get the stability of the molecules through the calculation of bond order. Now there are the few points, those are the principles of molecular orbital theory. So as we have seen in atomic orbitals, there are the electrons. So as the atoms combine with each other, molecule is formed. Similarly, when atomic orbitals combine with each other, molecular orbitals are formed. Atomic orbitals are in short form known as AOs, whereas molecular orbitals in short form are known as MOs. As atomic orbitals contain electrons, similarly molecular orbitals are also filled by electrons. Now the total number of atomic orbitals combined with each other is equal to total number of molecular orbital. The same number of molecular orbital we'll get. If two atomic orbitals combine with each other, we will get two molecular orbitals. If four atomic orbitals combine with each other, we get four molecular orbitals. Uh, so the total number of MOs remain the same. Now, out of the total number of MOs, half are the bonding MOs, that is, those are stabilized, known as the BMO in short form, and the half are the antibonding MOs, known as the ABMO. So, bonding MOs are the stabilized MO, and antibonding MOs are the destabilized MOs. So, the extent of bonding stability of the bonding MOs equal to the extent of destability of the antibonding MOs to balance the total energy of the system. Now, molecular orbitals are also filled by electrons following the same principles as we use to fill the atomic orbitals. Those are the above principle, the Pauli's exclusion principle, and the Hund's rule. So, in short, if I brief these principles, above principle is, that is, we have to fill the orbitals from lower energy, and then step by step we have to go to the higher energy orbitals by filling them by electrons. Now next is, what is Pauli's exclusion principle? That is, in one orbital there will be maximum of two electrons, and both those two electrons will be of opposite spin. And what is the Hund's rule? Hund's rule actually says that during the filling of orbitals by electrons, first the orbitals will be filled by one electron in each of same spin. When all the orbitals are filled by electrons of same spin, then only pairing will be occur in the orbitals. So now is, as I already mentioned, that atomic orbitals combine with each other to form the molecular orbital. Now this combination method is known as linear combination of atomic orbitals, in short LCAO method. Now if we consider, what is LCAO method? If we consider psi1, suppose psi1 is the wave function related with the atomic orbital of atom 1. And psi2 is the wave function related to the atomic orbital of atom 2. As you know from Schrodinger wave equation, orbitals can be considered as the uh, wave, and the wave is there is always wave function associated with the wave that is given by psi. So psi 1 related to the atom 1, psi 2 related to the atom 2. So when atom 1 combines with atom 2, similarly psi 1 also overlaps with psi 2. This overlapping may be of two types. One is the addition overlapping, psi1 plus psi2. This type of overlapping is also known as in-phase combination or constructive interference. That is, the two waves will be in the same phase when they overlap with each other. And in phase combination, this type of positive overlapping gives rise to the bonding molecular orbitals. So bonding molecular orbitals are of lower energy, stable. They are stable because they are generated due to the in-phase combination of the atomic orbitals. When the atomic orbitals combine in out-of-phase combination, that is subtraction mode, psi1 minus psi2, that is also known as destructive interference of the waves, that gives rise to antibonding molecular orbitals. As a result, antibonding molecular orbitals are of higher energy. So now is, which type of molecular orbitals do we get from the combination of atomic orbitals? That depend on which type of atomic orbitals are combined. We know there are the atomic orbitals like s orbital, which is spherical in shape, and p orbital, which is dumbbell in shape. Now when two s orbitals, suppose in this picture you can see two s orbitals combining with each other, they are spherical shape. These are the two AOs. This is one atomic orbital s orbital. This is another atomic orbital s orbital. When these two orbitals are combining in addition mode in phase combination, it gives rise to the sigma bonding MO. So it is the bonding MO, and bonding MO is denoted as sigma, and as this sigma comes from the overlapping of s orbital, so it is called sigma s orbital, and add it is the addition combination, so the total size of the orbital, here you can see the molecular orbital, the total size increases. Both the AOs were of positive sign, so the MO we get also having positive sign. Now when they overlap in destructive ways, destructive fashion, you can see, so one is positive, minus positive, or you can take plus negative. Then what happens at the middle, you can see there is the no orbital, no electron. It is called the nodal plane. So what is node? Node is the position where probability of finding electron is 0. So at the nodal point, there will not be any probability of finding electron or orbital. So you can see on the opposite side of the node, there is the opposite symmetry. One side is the left side positive symmetry, right side lobe is negative symmetry. So this type of MO is formed. This is the unstable MO, and this is the antibonding MO, and it is, as the bonding MO was sigma, so it is the sigma star. So antibonding MO always denoted by the star sign. Star represents here instability or higher energy state. So it is the bonding was sigma s, so the antibonding becomes sigma s star. Only star sign to be used to denote as the antibonding MO. So these are the shapes of the bonding and antibonding MO. Here you can see two AOs are combining, two s orbitals are combining. So we are getting two MOs. One is the sigma s, another one is the sigma s star. Now similar combination also we get for the s and px. S orbital and the px orbital. We know there are three p orbital. One is the px, py, pz. So if we take the axis 3D axis like this, x along the horizontal axis, y and z are the vertical axes, then the px will remain along the x-axis like this. This is the px orbital. Py orbital will remain like this, and pz orbital remain oriented like this along the pz. Z axis. So S orbital, that is spherical in shape, and Px orbital, dumbbell in shape, when combined with each other, that also gives rise to two sigma MOs. One is sigma MO, another is sigma star MO. But in case of Py and Py combination, or Pz on Pz combination, what happens? So suppose this is one px or py orbital, suppose this is one py and this is another py. They are combining with each other. So you can see both are vertical. When they combine with each other, this type of combination between them is called lateral overlapping or sidewise overlapping. You can see here they are overlapping with each other in sidewise fashion. So what happens? This type of overlapping will generate pi molecular orbital. So you see here the positive lobes will combine with each other. The total size of the positive lobe increases, whereas the negative lobes combine with each other. Total size of the negative lobe in the MO increases. So this is the shape of the pi MO. And there is one nodal plane at the middle of the both the lobes of opposite sign. As we observed is also for AO there was the nodal plane, also for MO there is the nodal plane. Now when there is the destructive interference or out of phase combination between them, the lateral overlapping between out of phase lateral overlapping between them, then what happens here? You can see the positive lobe combines with the negative lobe and here, so it gives rise to the pi star antibonding MO. In total, four lobes are formed here, two positive and two negative, and the two nodal planes are there. Already one nodal plane exists, that is this one, and another nodal plane here generated, that is the vertical nodal plane here generated for the pi star. So for the pi star p orbital, there is the two nodal planes. So this type of P for Py we get the pi MO, and for PZ combination also we get the pi MO, whereas for the SS combination we get sigma MO. This SS overlapping is known as head-on overlapping. This head-on overlapping is very strong than the lateral overlapping. So S orbital, the sigma orbitals are always stable than the pi orbitals, because head-on overlapping is always more stronger than the sidewise overlapping. So when we go to the molecular orbital, we will observe sigma MO always present at lower side than the pi MO, because they are more stable. Now going to the simplest case, that is the construction of MO for hydrogen molecule, H2 molecule. So you know there the hydrogen is formed by combination of two hydrogen atom. This is one hydrogen atom and there is another hydrogen atom. One hydrogen atom contains one electron. So this is the 1s of one hydrogen atom. This is the 1s of another hydrogen atom, and each having one electron each. Now when they combine with each other as two AOs are there, the two MOs will be formed. At the middle the MO is shown here. One is the bonding MO, another one is the antibonding MO. So as here S orbitals are combined, so we get here the sigma bonding and the sigma star antibonding orbitals. Sigma and sigma star. Now as there are the two electrons, so how to fill them? First we have to start from the lower energy, will go to higher energy. Each orbital will have maximum 2 electrons. So as there are the 2 electrons, so both the electrons we have to put in the lower energy orbital, that is sigma orbital. So this is the MO diagram of H2 molecule. Now how to calculate the bond order? Very important parameter that is obtained from the molecular orbital. So what is the formula? Number of electrons in bonding molecule minus number of electrons in antibonding orbital divided by 2. So for H2 molecule, you can see how many bonding orbital are there. There is the one, this one is the bonding orbital and this one is the antibonding orbital. So how many electrons are there in bonding MO, that is sigma MO? There is 2 electron. And in antibonding MO sigma star, there is no electron. So what is the formula? For hydrogen, the formula becomes for bond order 2 minus 0 divided by 2. So what we are getting here, 2 by 2, that is bond order is, for hydrogen the bond order is 1. So you can see here for hydrogen the bond order is 1. Similarly, if we go to the He2 molecule. He2, we know the electronic configuration is for helium atom 2s1s2. So here you can see one 1s of one helium, another 1s of another helium. When they combining, again similarly two MOs are formed. One is the sigma MO, this one is the sigma, and this one is the sigma star antibonding MO. In total, how many electrons? 2 here and 2 here. So total 4 electrons. How to fill them? 2 electrons in bonding, 2 are in antibonding. So what is the bond order of He2? 2 minus 2 by 2, that is 0. So He2, as the bond order is 0, actually bond order says how many bonds are present between atoms. If one bond is present, bond order is 1, means one bond, means it is single bonded molecule. If bond order is 0, means there is no bond between the atoms. So that means that molecule does not exist. He2 molecule actually does not exist. As we know, it is noble gas, so it cannot form molecule. Now we go to the bond order of He2 plus, H2 plus, sorry, H2 plus. What happens here? As here one positive charge is there, so one electron we have to remove. Positive charge means removal of electron, negative charge means addition of electrons. So one electron we have to remove here. So from where to remove the electron? The rule is that you have to remember, the rule is from the highest energy field orbital we have to remove the electron. When we are adding electron, also we have to add electron to the highest energy partially filled or empty orbital. So we are adding electron to the partially filled or empty orbital, then there will be negative sign and it is the highest energy orbital. When we are removing electron, that we have to remove from the also from the partially filled or totally filled orbital, that should be also highest energy orbital. So for H2 plus, here the removal of electron will be from sigma only, it is sigma. So one electron is removed, so there remains only one electron. So what would be the bond order? 1 minus 0 by 2, that you can see 0.5. Similarly for He2 plus, you can see here one electron, from where to remove the electron? The electron to be removed from the highest energy orbital. Yeah, sigma star has higher energy, so you have to remove the electron. There is one electron, and in bonding there are the two electrons. So the bond order is 2 minus 1 by 1, that is 0.5. So He2 plus, the bond order is lower than He2. He2 is 0, sorry, higher than He2. He2 is 0, He2 plus 0.5. So you can see He2 plus is more stable than He2. So bond order higher means higher stability, bond order lower, lower stability. Similarly, H2 bond order is 1, H2 plus bond order is 0.5. So what is the stability order? H2 is more stable than H2 plus. That means He2 plus it can exist, whereas He2 does not exist. So from the bond order calculation, we can predict the stability. So this slide already I have discussed, that is the when the px combines, there is formation of two sigma bonds, sigma p and sigma star p. When py combines with each other, that gives rise to the two pi molecular orbitals, pi p and pi star p. Similarly, when pz combines, pi and pi star are formed. That is already discussed. Now going to the next MO, that is the molecular orbital diagram of oxygen molecule. Now you see here for one oxygen atom, what is the electronic configuration? 1s2, 2s2, 2p, 4. So this is the atomic orbitals of one oxygen atom. This is atomic orbital of another oxygen atom. So when they are combining with each other, at the middle the O2 MOs are formed. Now first go to the 2s atomic orbitals of the two oxygen. These 2s and these 2s combining with each other, two MOs will be formed. One is the sigma 2s, another one is the sigma star 2s. One is bonding, another one is anti-bonding. Now going to the p orbitals. How many p orbitals are there? Here are the 3 p orbitals, and for another oxygen molecule there are 3 p orbitals. So 3 plus 3 total 6 orbitals combining with each other. So how many MOs do you expect total? 6 MOs. So out of those 6 MOs, as per the rule, 3 are the bonding MOs stable, 3 are the anti-bonding MOs unstable. Now you see, out of the 3 MOs, 2 p orbitals, that is I already discussed, px and px combine to form the sigma orbital, whereas py and pz combine to form the pi orbitals. So one sigma is formed. As I said, sigma combination is more stable, more stronger combination. So sigma orbital is lower in energy, it is more stable than pi. And here one interesting thing is the 2 pi orbitals, those are degenerate, that is having same energy, because their orbit, their interaction, the formation fashion is same. The interaction of atomic orbital, that fashion is also same. So that gives rise to 2 pi orbitals of similar energy, that is called degenerate orbitals. Similarly, the corresponding to that 2 pi star orbitals are formed. Those are also have same energy, and there is one sigma star orbital that is of highest energy. So this is the MO order of the oxygen molecule. Now we have to fill them by electrons. So in total you can see for one oxygen atom 6 electrons, for another oxygen atom 6 electrons. So in total there are 12 electrons. So now first you consider the electrons of the atomic orbitals. Now you take how many total electrons, then you fill them in the MOs stepwise. So in total 12 electrons are there. Now how to fill the MOs? First we start from lowest energy, that is sigma 2s. How many? 2 electrons. Then sigma star 2 electrons, then sigma 2pz 2 electrons. Then we'll go to the pi. How to fill the pi? As they are degenerate, so first one here, another one is here, again we'll come back here pairing and here pairing. So one by one we have to fill them. After that, so in total 12, so 2, this is the 2, this is 4, this one is the 6, 8, 10. So 2 electrons in our hand, we have to put them in the pi star orbital. How to put them? One in the pi star 2px, another one is the pi star 2py. One is pi star 2px, another one is the pi star 2py. So this is the filling of electrons. Now calculate bond order. Bond order is bonding minus anti-bonding. So which are the bonding orbitals? This one is bonding here. Sigma 2s is bonding. Sigma 2pz is the bonding. Pi 2py and pi 2pz are bonding. So total bonding electrons 2 plus 2 4, 6, 8. So 8 are the bonding electrons. Anti-bonding, which are anti-bonding, I am giving cross sign. So sigma star 2s and pi star 2py 2pz. So total is 4. So 8 minus 4 by 2. What we are getting? 2. So bond order is 2. As we know, oxygen is double bonded. There is double bond present exists between the two oxygen molecule. And also from here we can guess the magnetism, as there are the two unpaired electron here in oxygen, two unpaired electrons, very important. So oxygen molecule is paramagnetic. We also know it is paramagnetic. If there is unpaired electron, it is paramagnetic. If all the electrons are paired, it is diamagnetic. Now, if we consider the O2 plus species, for O2 plus species, what happens? We have to remove one electron, as there is one positive sign. So, from where to remove the electron? We have to remove from this electron, we have to remove from the highest energy orbital. So, if you remove this electron, then in antibonding orbitals, there are 3 electrons. So, it becomes 8 minus 3 by 2. So, it becomes 2.5. Now O2 minus, what we have to do? We have to add one electron as there is negative sign. Where to add the electron? For O2 minus, we will add the electron here in this orbital to the highest energy orbital. As this pi px py are the degenerate orbital, so you have to put the electron here. So here you can put the electron in px or py, those are similar. So now putting the electron, what happens? Now the total antibonding becomes 5. So 8 minus 5 by 2, it becomes 1.5. Now O2 2 minus, that means another one electron you have to add. So for O2 2 minus, another one electron you have to add here. So now the antibonding electrons becomes how many? 6. So 8 minus 6 by 2, that is 1. So you can see the stability, the bond order of O2 plus is maximum. So O2 plus is maximum stable. Then O2 it is 2. Then O2 minus stable. Then O2 2 minus, as we know, it is peroxide, very much unstable. Whereas O2 minus is superoxide, it is stable than peroxide. So now going to the MO of nitrogen molecule. So nitrogen molecule, here we can see the MO all over the MO diagram is same. Only difference you can see here in the order of sigma and pi MOs. For oxygen we have seen sigma was lower than pi. Here we see the sigma, that this sigma orbital is higher than these pi orbitals. Why? Due to some secondary interaction here. Secondary interaction between the sigma 2pz and the sigma 2s. This sigma 2s and this sigma 2pz, they, due to secondary interaction, what happens? This sigma 2s becomes more lower in energy, and this sigma 2pz, that becomes higher in energy. It crosses the energy of pi. So pi to px, pi to py becomes lower, and whereas the pz, sigma to pz, becomes higher in energy. And the other bond order, all the order of the MOs remains the same. So only difference is here in this part for the nitrogen molecule. So now you can again fill them by electrons. So in nitrogen, you know 2s2, what is the configuration? 1s2, 2s2, 2p3. So in total, how many electrons? One nitrogen atom means 7 electrons. So in total 14 electrons. How to fill them? Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Now going to the pi orbital, pi to px1, pi to py1, pi to px2, pi to py2, then sigma to pz2. So 14 electrons, 2 plus 2, 4, 6, this is 8, 10 plus 10, 2, 12, and this one is 14. So total 14 electrons. How to calculate the bond order? So you can calculate it, 10 minus 4 by 2, that is 3. You know it is triple bonded molecule. Similarly, you can calculate the bond order of N2 plus 2.5. You have to remove, for N2 plus, you have to remove the electron from the sigma 2pz. One electron you will remove. For N2 2 plus, N2 2 plus, both the electrons of the sigma 2pz, you have to remove both the electrons. N2 minus, you have to add one electron. For N2 minus, where to add the electron? For N2 minus, as it is the highest energy backend orbital, so you will add the electron here. Now you calculate bond order, it becomes 2.5. For N2 2 minus, where to add the electron? You have to add the electron in another pi orbital. Now you calculate bond order 2. So similarly, you can give the stability of this species. So here you see, for hydrogen to nitrogen molecules, hydrogen, very important to remember, hydrogen to nitrogen, the molecular orbital order is like this: sigma 1s, sigma star 1s, sigma 2s, increasing order, sigma star 2s. After that there comes the pi orbitals, both are degenerate having same energy, so equal sign, then sigma 2pz, then pi star, then sigma star. for oxygen to neon, oxygen, fluorine, neon, those are having the similar energy diagram. What is that? All are same, only difference is, as I said, sigma becomes lower than pi. So here sigma is lower and pi are the of higher energy. So this type of MO diagram is followed for oxygen, fluorine and Ne2, neon. And for hydrogen to N2, hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen. Actually, lithium, beryllium, there is no p orbital, so no need of considering those MOs. From boron B2 molecule, we have to consider this MO diagram. B2, C2 and N2, this MO diagram to be followed. Now going to the pi MO formation. So pi MOs of, we will consider here only two molecules according to the syllabus, BTech syllabus. One is the 1,3-butadiene, another one is benzene. So let's first consider the 1,3-butadiene molecule. This is the structure of 1,3-butadiene. There are 4 carbon atoms. This is the first carbon, this one is the second carbon, this is the third carbon, and this one is the fourth carbon. How many double bonds are there? 2 double bonds. So one double bond means there is one pi bond, and one pi bond means how many p orbitals? There are the 2 p orbitals which are non-overlap. They are the pure p orbitals. So this pi bond means there is the 2 p orbital. Similarly, this pi bond means there are the 2 unoverlapped p orbitals. So in total there are the 4 p orbitals present in the butadiene, which are non-hybridized orbitals. So for p orbitals, here we will consider only the pi MOs. Though in 1,3-butadiene there are the sigma bond, sigma MOs, but we are considering here only the pi MOs. We will focus only the pi MO formation. So for p orbitals, those will combine to form 4 MOs. As we know, the number of AOs and number of MOs remain the same. So here the 4 unhybridized p orbitals will give rise to 4 MOs: pi 1, pi 2, pi 3 and pi 4. Pi 1 has the lowest energy, pi 4 has the maximum energy. Now you see pi 1, it has node 0. Node, I already said, probability of finding electron is 0. And if we consider node, another thing is on the two sides of the node there will be opposite symmetry. Very important, you have to remember, two sides of node has opposite symmetry. So for pi 1, node is 0. Node 0 means all the orbitals will have same energy. So if we consider C1, C2, C3, C4 of butadiene, these are the 4 C of butadiene. So for the C1, the orbital, the shaded lobe in the lower side, the unshaded lobe upper side. For C2 also similar, C3, C4 similar, as there is no node. So all the orbitals having same symmetry. Now go to the pi 2. As we go one by one, as we go to the higher energy, the number of node increases one by one. So in case of pi 2, there will be one node. One node means where to put the node. We have to put the node such that there will be maximum symmetry in the total MO. So at the middle we have to put the node. So this is the node, that the dotted red line that is showing as the node. So on the two sides of node there will be opposite symmetry. So left side you can see the two lobes, shaded lobes in the lower side, and right side you can see the shaded lobes on the upper side. So you can take, that is your choice, which one you can take, lower or upper, but the two sides will be of opposite symmetry. Similarly, going to pi 3, how many nodes will be there? 2, obviously. So 2 nodes where to put. One node will be after C1 and another node will be after C3. So C1, as there is the node, this one shaded lobe lower side, this one will be shaded lobe upper side. C3 also shaded lobe upper side, as there is no node between these two carbons. These two carbons, there is no node. So similar symmetry. Now the C4, the shaded lobe will be lower side. Now going to the highest energy orbital, that is pi 4, node is equal to here 3. So all the between two carbons one node is present. So all the carbons having opposite symmetry, C1 shaded lower side, C2 upper, in this way all are having opposite symmetry. So now is these are the MO diagram of the 1,3-butadiene. Now the question, how to fill them by electrons. So as there are the two pi uh, bonds, one bond means 2 electrons, so 2 pi bonds means there are 4 electrons. So 4 pi electrons are present. Only we are considering pi electrons. Again I am saying. So how to fill them? From we have to start from the maintaining the same rule, following the same rule from lowest energy. So the pi 1 we have to put 2 electrons, and the pi 2 we have to put another 2 electrons. And the pi 2 is the highest occupied molecular orbitals, because here how many molecular orbitals are occupied by electron? Pi 2 and pi 1. Pi 2 and pi 1 are filled. Among them pi 2 is the highest one according to energy, so it is the HOMO, it is called HOMO. And LUMO, lowest unoccupied molecular orbital. What does it mean? Which are unoccupied here? Pi 4 and pi 3. These two are unfilled or unoccupied. Among them, which one is lowest in energy? That is pi 3. So pi 3 is called LUMO. Now going to the molecular orbital, pi molecular orbital of benzene. So we know the structure of benzene. There are how many pi bonds in benzene? 3 pi bonds. 3 pi bonds means how many p orbitals? 6 p orbitals. 6 p orbitals combine to form 6 MOs. 6 MOs combine to form 6 MOs. 3 are bonding, 3 are anti-bonding as usual. Among these three, the pi 1 is the lowest bonding orbital. So for pi 1, obviously node is 0, there is no node, so you can see all the p orbitals having the same energy, all having the upper lobe shaded. Node is 0. Now going to the next two orbitals, pi 2 and pi 3, they are degenerate orbital for benzene. So both of them having node 1. So for pi 2, if we consider the node as the vertical line, for pi 3 the node will be of the horizontal line. For pi 2, as the node is vertical, so opposite side you can see the left side, right side, opposite symmetry. For pi 3, the horizontal line actually it represents the nodal plane, like a blade. You just think that one blade like thing you are passing through the ring. So what happens? The lobes present at this position and this position, those lobes, you are cutting those lobes, so you cannot see those lobes. So only these four lobes are there, and they are on the two sides of the node, so they are having opposite symmetry. So these two orbitals having the symmetry, the lower two orbitals having opposite symmetry. So these are pi 2, pi 3. Now going to the antibonding orbitals, pi 4 star and pi 5 star. How many nodes will be there? Two nodes. So how to put the nodes? The diagonal fashion, here you have in pi 4 star two diagonal nodes are there, and on the opposite side there will be the, on two sides of the node there will be the opposite lobes, so opposite symmetry. So you can draw in pi 4 star, in pi 5 star, the two nodes are like one is vertical, another one is horizontal. So one node is in the vertical fashion, or another one is the horizontal nodal plane, as in case of pi 3. So here also the maintaining the symmetry, opposite symmetry on the two sides of the node. Now going to the highest energy orbital, pi 6 star. How many nodes will be there? 3 nodes. Where to put two diagonal? One is the vertical. So 3 nodes, all the orbitals having their opposite symmetry, because the node is passing between all the two successive orbitals. Now how many pi electrons are there? In benzene there are 3p pi orbitals. So 6 pi electrons are there. Where to put? Pi 1, pi 2 and pi 3. So which are the HOMO for benzene? Pi 2 and pi 3 are the HOMO for benzene. For benzene, so these are the HOMO of um, And for the pi 4 star and pi 5 star, these are the LUMO for benzene. These are LUMO, lowest unoccupied molecular orbital. So these are the pi-MO diagrams of benzene. So this is all about the molecular orbital theory. And what are the importance? So the as already I discussed, from molecular orbital theory we can say about the covalent bonding formation, we can say about the stability of molecules, we can explain the delocalization of electrons as well as magnetic behavior, whereas the molecule is paramagnetic, diamagnetic can be explained. Also, it helps to understand the spectra, UV visible electronic spectra, because as there is a lower and higher energy orbitals, by promoting the electrons we get the spectra. So this is all about the molecular orbital theory. Thank you.